Hello. In this video, we will be discussing group actions, cosets of subgroups, Lagrange's theorem, and its applications to classical number theory. For instance, Euler's theorem and Fermat's little theorem. Arguably, this is one of the most important parts of basic group theory. One can say that one cannot understand a group without its actions. Okay, let's try to understand what is group action. In order to motivate definition of group actions, let's go back to how we motivated group theory. As we have mentioned many times, group theory is about understanding symmetries of objects. The meta-example that we have for groups is symmetries of an object X. Now, we can ask ourselves, can we go backward? I give you a group G, and I give you an object X. Can I think about this group G as symmetries of this object X? What does that mean? We want to think about elements of G as functions from X to X in a way that the composition of functions would be compatible with the group operation of G. Now, the easiest of the objects, as we have discussed earlier, is when the object X is just a set with no additional information. Then what we are asking is, can I think about G as permutations on the set X? What if I relax and allow some of the elements of G to act like identity? Do not move anything. Then what? Can I still understand G as certain permutations to be compatible with the group operation? One way of formulating this compatible with group operation is, of course, asking whether or not we have a group homomorphism from G to the symmetric group of the set X. Here I am going to take another route, which is more classical, and define the group action. So let's say I give you a group G, and I give you a non-empty set X. When we say G acts on X via certain map, this map star, we are going to denote it by a star right now, takes an element of G and an element of X and asks what kind of permutation does this element G do to this element X. We say, how does this element G act on X, small element X? We say that this star is indeed a group action if the following properties hold. The first one says that the neutral element should act like the identity function, which means for every element small x in the set capital X, the neutral element star x is x. So it sends the point x to itself. It behaves like the identity function. The second condition says that this action is compatible with the group operation. Which means what? Which means if I give you G1 and G2 in the group and an arbitrary point inside this set capital X, if we allow the element G2 act on X, wherever it goes, we allow G1 act on that point, this should be the same as applying the point, the element G1 dot G2 to the point X. So in that sense, we say the action that's given by star is compatible. The permutation that we get out of the star is compatible with the group operation. Whenever we have a function star with these properties, we say that G acts on the set X via a star. And we simply write it like this. So we say G acts, we use this curly arrow on the set X, and sometimes we indicate that the action is given via the function star. So we put the star below the arrow in order to indicate what the action is. Sometimes we don't put the star at all and simply say that G acts on X when the action is clear from the context. Okay, now let me also point out that often in maybe earlier in this course, later in this course as well, but in more advanced texts, we use again dot for the group action. Here I try to avoid it to make it more clear and to distinguish it, to distinguish the action that we have here, distinguish it from the multiplication of the group. But as we can see here, because of these compatibility, even if I denote it by dot, it is okay. There is no confusion in the equations in a sense. But if we use the dot, you have to still know why we have the equalities. This equality is not because we have associativity. It doesn't make sense. Associativity is about a single operation in a single set. Here we have two sets and two different operations. So still I encourage you to use star instead of dot, but in more advanced texts, we often use dot for the group action as well. Okay, so let's see some examples of group actions. We start with the generic one, the general one, the group of permutations. So suppose X is a non-empty set, and I am going to take its group of symmetries. In this case, it means the symmetric group. Then the symmetric group acts on X, and what is the action? What is the action map? It acts via the following star. When I give you a permutation and a point inside this set, then I'm getting a new point because sigma is a permutation. I let it act on X. I apply sigma to X, and I get sigma of X. That's another point inside X. I denote this by a star, and my claim is that this is actually giving me an action of S sub X on the set X. Let's check why this is the case. I start with the first condition. I pick the neutral element of this, which is the identity map. So we pick the identity map and let it act on an arbitrary point. By definition, I have to apply the identity function to the point X. By definition, identity function doesn't move any point, so I get back X. So for every X, I get the first condition. Identity star X is X. Now let's pick two permutations, sigma 1 and sigma 2, two elements of the symmetric group. And then I need to apply sigma 2 and then sigma 1 to an arbitrary point X and see what we get. When I apply sigma 2, by definition, I have to apply sigma 2 to the point X. And then when I let sigma 1 act on this point, that means that I need to apply sigma 1 to the point sigma 2 of X. That means I'm looking at the composite of sigma 1 and sigma 2 and apply it to the point X, which means we are letting the composite of sigma 1 and sigma 2 act on the point X. And we get the desired equality. So this is indeed a group action, and so to speak, this is a fairly general group action. I can replace this by the group of symmetries. Instead of this, I can put the group of symmetries and arbitrary object X and let it act on that object, and one can check these properties in an identical way. Now let's look at the following example, which is of more abstract nature. So I give you a group, an abstract group. It's an arbitrary group. let's say a multiplicative group, it's is given by the dot notation. Then this set, this group, acts on itself via left multiplication. In fact, this is how we proved Cayley's theorem. We let it act on itself by left multiplication. But let's try to understand it. What do I mean that I let it act by left multiplication? This means for an element of the group G and a point inside the set G, G star X, the way that this element acts on the point X is simply by multiplying X by G from left. So both of them are in the group G. I can multiply them, and that's my group action. Okay, let's see why it satisfies the two conditions of group actions. Let's start with the neutral element. You have to say that neutral element acts trivially on all the points of the set. That means I need to show that the neutral element star X is X. But what is this star? It simply means that I need to multiply the neutral element by the element X inside the group G. By the definition of the neutral element, I know that EG dot X is simply X, and that's exactly the condition that we were looking for. Next, I need to show that G1 star parentheses G2 star X is the same as G1 dot G2X. But let's go step by step. G2 star X is simply G2 times X inside the group. I get another point inside the group, and then I need to understand what is G1 star of this point. Again, by definition of a star, in this case, G1 acts by left multiplication. I simply need to multiply G1 from left by G2 dot X. Now I can use associativity because both of these dots are multiplication in the group G, and I know that this operation is associative. That means I can reorder the parentheses, and I get that it is G1 dot G2 multiplied by X. That's the definition of the action of G1 dot G2 on the point X, and we get the desired equality of group actions. So left multiplication is another action of G on itself, is an action of a group G on itself. Let me give you another action of the group G on itself. This one is by conjugation. So G acts on itself via conjugation. What does that mean? This means I give you an element G, and I give you a point X. Element G is inside the group. The point X is also inside the group, but I'm thinking about this as a set this time, not as a group. So now, how does this element of the group act on this point? It simply conjugates it. So what I end up getting is this, G times X times G inverse. We simply say that I'm conjugating X by G. So this action is called conjugation. So G acts on itself by conjugation. Again, let's check why it is indeed a group action. So I start with a neutral element. Let's see why the neutral element acts like the identity function. So let the neutral element act on the point X. This means I need to conjugate X by the neutral element. I need to conjugate X by the neutral element, which means I need to multiply it from by E sub G from left and by E sub G inverse from right. But remember, E sub G inverse is the neutral element anyway. So in any case, we end up getting X back. And that's exactly what we wanted to get. Okay, next let's check what we have when we apply G1 to what G2 does to X. Let's start with the inside parentheses. When I apply G2 to X, when G2 acts on X, that means I'm simply conjugating X by G2. I'm conjugating X by G2. Now, when I apply G1 to this element, I have to conjugate this element by G1. So I'm conjugating this element by G1. Now, the whole operation is done in the group. In group, operation dot is associative, so I can reorder the parentheses. Here, I simply get G1 times G2. I have X in the middle, and then I get G2 inverse, G1 inverse. And remember, G2 inverse, G1 inverse is G1, G2 inverse. So that means I'm conjugating X by G1, G2. And that is how G1, G2 acts on X. So we get the desired equality that when G2 acts on X and then G1 acts on it is the same as G1 times G2 acts on X. So therefore, it is indeed a group action. Now, suppose that I have an action, G acts on X. Initially, when I wanted to motivate group action, I mentioned that it should permute elements of X, and this permutation should be compatible with the group operation. Let's make sense of this. Am I really getting a permutation? So suppose that this is an action. Then for every element of the group, I'm going to look at the function from X to X that's induced by the action of the element G. So I let the element G act on the set X, and I end up getting a function from X to X. Let's denote this function by sigma sub G. So sigma sub G is a function from the set X to itself, and this function sends the point X to what G does to it. So we are asking how this element G acts on the set capital X. Now let's make some observations. For instance, what kind of map am I getting for the neutral element? When I look at neutral element, sigma sub neutral element, and I apply it to X, it means how does the neutral element act on the point X? By one of the properties of group action, I know that E sub G star X is simply X, which means sigma sub neutral element is simply the identity function from X to X. Now let's see what the second condition of group actions implies here. I give you two elements of the group. Then we need to let G2 act and then G1 act. That means essentially I'm looking at the composite of these two functions, sigma sub G2, sigma sub G1 composed with sigma sub G2. That means I'm first letting G2 act on X and then letting G1 act on X. But let's actually explicitly write it down. Sigma sub G2 of X is what G2 does to X. And then I apply this one to this point, and that means what G1 does to what G2 had done to X. Now, by the second property of group actions, I know that this is what G1 dot G2 does to X. And that's by definition sigma sub G1 G2 applied to X. Both of these functions, this one and this one, are functions from X to X, and they are giving us the same rule, and therefore they are the same functions. In particular, I deduce that when I look at the composite of sigma sub G and sigma sub G inverse, I'm getting sigma of G dot G inverse, which is sigma of the neutral element, and that we showed to be the identity function. Similarly, when I look at the composite of sigma G inverse and sigma G, we end up getting the identity function. That implies that sigma of G, sigma sub G, is a bijection, is an invertible function, is a bijection from X to X. Therefore, it belongs to the symmetric group of X. So this is exactly what we claimed initially, that group actions give us permutations on the set X. So if G acts on the set X via star, then sigma sub G that's given by the action of the element G is a permutation, is a bijection, and therefore it belongs to S sub X. Now the next theorem tells us that in fact this compatibility thing gives us a group homomorphism from the group G to the symmetric group. So if G acts on a set X through the action star, and if I define f to be the function, so this function is it might be slightly confusing, so please pay attention. So I feed f an element G. It spills out a function. It spills out a permutation. So f of G, which we denote is sigma sub G. Remember, sigma sub G is a bijective function from X to X, and therefore it belongs to the symmetric group of X. Sigma sub G itself is a function. It's a function from X to X. It's a bijective function from X to X, and therefore it belongs to the symmetric group of X. So f is a function from G to the symmetric group of X, and claim is that this function is a group homomorphism. Proof of this theorem is rather easy. Understanding what it says might be more subtle. Okay, so let's see why this statement is true. We simply need to show why f of G belongs here. That one we have already discussed, and show that f preserves group operation. That means I need to show that f of G1 dot G2 is f of G1 composed with f of G2. Okay, let's see why this is the case. F of G1 dot G2, by definition, is a sigma of G1 dot G2. But remember, we have already proved that sigma of G1 dot G2 is the composite of sigma of G1 and sigma of G2. So this is simply the composite of sigma of G1 and sigma of G2. So I get sigma of G1 O, sigma sub G2. Sigma sub G1 is f of G1, and sigma sub G2 is f of G2. So we are getting the composite of f of G1 and f of G2. That's exactly the definition of a group homomorphism. So f of G1 dot G2 is the composite of f of G1 and f of G2, and therefore f is a group homomorphism. The converse of this theorem is also true, that if I start with a group homomorphism from G to the symmetric group of X, then I can define an appropriate group action of G on X, but that one we are not going to discuss here. So here we showed that a group action gives us a group homomorphism from G to the symmetric group of X. Let's see another example of group actions, which is important for us because we want to understand cosets of subgroups. Suppose that I give you a group G, and I let you know that it acts on a set X through some map, via some map X, a star. And let's say I tell you that H is a subgroup of G. Then the same star let H act on the same set X. I can restrict the action of G to an action of H. Okay, let's try to understand. Only one point might be a bit subtle. Because H is a subgroup of G, we know that they share neutral elements. So neutral element of H is simply the neutral element of G. This is what we proved earlier when we discussed subgroups. Therefore, the first part, the first condition for group action, now we have for free. For every x inside the set capital X, the way that neutral element of H acts on it is the same as the way that neutral element of G acts on it, because these are the same elements anyway. And because G acts on X, I know that this action is just a trivial function. Now, when I give you two elements of the group H, and I want to check whether this star action is compatible with the group operation of the group H, we simply use the fact that the star action is compatible with multiplication inside the group G. And notice that because H is a subgroup of G, multiplication in H is the multiplication in G. So if I give you two elements of H, then they are elements of G, and multiplication in G is the same as multiplication in H, because H is a subgroup of G. Therefore, because the star is a group action, G group action, I know that this is the same as H1 times H2. This multiplication happens inside the group G. But we know capital H is a subgroup of the group G, and therefore this multiplication can be viewed as a multiplication in the subgroup H, and we get the desired equality. Okay, so if I have an action of the larger group, then we get an action for all the subgroups. Let's see this, what it does to cyclic subgroups of the symmetric group. We know that S sub n, the symmetric group, the nth symmetric group, acts on the set 1 to n that we have discussed earlier. The symmetric group of the set X acts on the set X by simply letting the function applied to the point I. Now, the cyclic subgroup generated by sigma is a subgroup of S sub n, and therefore the action of S sub n on this set gives us an action of the cyclic group on this set. Okay, again, because S sub n acts on this set via this star action, which is simply letting the function tau, applying the function tau on the point I, we get an action of this cyclic group on this set. Now, let's also recall how we understood cycle decomposition of sigma, and we see the similarity between this action and that following flow rule for understanding cycle decomposition of a permutation. When we say that we want to follow the flow, that meant that we start with a point and then we apply sigma, then again apply sigma, then again apply sigma. We continue this, and at some point we showed that we are going to go back to where we have started. Now, if I want to say this in terms of action, this is simply how sigma acts on A. This one is how sigma squared acts on A, and so on. So I am saying that this cycle that we got out of there can be said that how sigma acts on the point A again and again and again, and where we end up getting, what we end up getting by letting sigma act on this point again and again. So this means that the whole set is what we can end up getting by applying integer powers of sigma to the point A. So these are all the possible points that we can get. Now, if I think about it and try to use the language of symmetries, it is the same as saying that try to imagine a structure where only sigma can give us, or powers of sigma can give us symmetries of that structure. So something like a cycle. So in cycle we also have tau, but for now let's think about a cycle now. Now, what we are saying is what points are similar, sigma to the I similar to A, using this type of symmetries, to what other points can we reach? So if I can reach to a new point, then that point should be sigma to the I similar to the point that I have started with. Okay, so this means this cycle decomposition are telling me what are the points that look like other ones if I only use powers of sigma. So for instance, if a point is fixed under sigma, this point doesn't move under sigma, so no other point is going to be similar to this point by applying some power of sigma. This is kind of fixed. This is different from the rest from the sigma point of view. Okay, so we can again interpret that if we only use symmetries that are induced by the cyclic group generated by sigma. So I'm saying that if we only use symmetries that are induced by this, what points are similar to A? Now, this brings us to the definition of G orbits for an action of G on a set X. So again, I'm letting G act on this set X, but then I don't allow all the other symmetries. I just focus on G, and I ask myself, if I start with a point small x, what other points are G similar to this point? If I just use symmetries using the elements of this group, to what other points of this set X can I reach? Those points we are going to call G orbits. But let's make it more precise again. We say 2 points X and Y of this set are G similar. They are similar to each other using the symmetries that come from the group G. And we write it like this, that X is in relation to Y. And what is this relation? Is G similarity. If there exists some symmetry that comes from the group G, and this symmetry acts on the point X and gives us Y. So if I let this element G act on the point X, to what other points can I reach? If I can reach to the point Y, I call it that I say that Y is G similar to X. Now the set of all the points that are G similar to X is denoted by G star X. So this is the set of all the points that are G similar to X. And we also call this set the G orbit of the point X. Sometimes we write it as O sub X, O standing for orbit. Now, the next theorem gives us a fairly good understanding of the set of G orbits and the set of all the G orbits and so on. The first thing is that this G similarity relation is in fact an equivalent relation. So G similarity is an equivalent relation. And therefore, the set of all the points that are G similar to a point X is indeed the equivalent class of X. So the G orbit of X is the equivalent class of X under the similarity relation, G similarity relation. In particular, the set of all the orbits form a partition of the set X. So the set of all the orbits, all the G orbits, is a partition of X. Okay, let's try to prove this theorem, which plays an important role in this course. So pay special attention to this, both understand how the proof goes, and more importantly, you need to understand many examples and how to use this result. Let's start by showing why this G similarity that I'm going to denote this time by tilde sub G to indicate that I'm talking about the G similarity relation is an equivalent relation. Let's recall what equivalent means, and a relation is an equivalent relation if it is reflexive, symmetric, and transitive. Okay, let's start with reflexive. Why is this relation reflexive? Reflexive means what? I need to show why every point is G similar to itself. So G is similar to itself. I need to find an element of the group that sends X to itself. The neutral element. So G is similar to the action of neutral element acting on this point, but that is X, and that's exactly what we needed. So X is G similar to itself. Now, why is it symmetric? That means what? If Y is G similar to X, can I show that X is G similar to Y? Okay, let's try to understand this. What does that mean that Y is G similar to X? That means Y is there exists some symmetry that comes from the group G that sends X to Y. So there exists G which acts on X and I end up getting Y. Now I want to go backward. Going backward means inverse of the element. So we simply look at G inverse. So we let G inverse act on Y. That means G inverse acts on what G does to X. Because of the compatibility of the group action and group operation, this is the same as G inverse times G acting on X. G inverse times G is the neutral element of the group, which acts like the identity function, and therefore we get that X, we can reach to X by applying an element of G to Y. That means X is G similar to Y. That's exactly what we wanted to show. So this shows that this G similarity is a symmetric relation. Now, finally, let's see why it is transitive. That means I'm going to assume Y is G similar to X, Z is G similar to Y, and I want to show that Z is G similar to X. Let's spell out each one of these conditions and what they mean. When we say Y is G similar to X, that means there is some element of the group that acts on X and sends it to Y. There is some symmetry that comes from G and sends X to Y. So there exists some symmetry that comes from the group G and sends X to Y. Similarly, because Z is G similar to Y, that means there exists some symmetry that comes from the group G and it sends Y to Z. Now I know how to go from X to Y. I know how to go from Y to Z. I want to go from X to Z. I need to compose these two together. I need to multiply them together. Okay, let's see why this is the case. So I start with Z. I know that I can reach to Z using G prime. I know how to reach to Y using G. So I get that this. But I know that group action is compatible with group operation. So this is equal to G prime dot G applied to X. That means I can reach to Z using G prime dot G from X. If I let this guy act on X, I get to Z. That means Z is G similar to X. That's exactly what we wanted to show. So we show that this similarity, G similarity, is reflexive, it's symmetric, and therefore transitive, and therefore it is an equivalent relation. By definition, the equivalent class of a point X under the similarity relation is the set of all the points that are in relation with X. That means all the points Y where X is G-similar to Y. So this is the definition of equivalent class of X. All the points Y where X is G-similar to Y. I want to show that this equivalent class is precisely the G-orbit of X. So I want to show equality of two sets. I have to start with one point in one of them, show that it belongs to the other one, and vice versa. Let's start with point inside the equivalent class of X. That means that X is G similar to Y. Now, because this is a symmetric relation, that also implies that Y is G similar to X. That means Y is G similar to X. Y is G acting on X for some element of the group small g. By definition, that implies that Y belongs to the G orbit of X. This shows that the equivalence class of X is a subset of the G orbit of X. Now I want to show the other way around. I pick something inside the G orbit. That means Z is G similar to X. Z is some element of the group acting on the point X. Again, let's think about this. What does that mean? This means Z is G similar to X. This G similarity is a symmetric relation. So X is also G similar to Z, and therefore Z is in relation to X. We get this inclusion, and therefore the G orbit of X is a subset of the equivalence class of X. These two together imply the equality of the sets that we were looking for. Therefore, every G orbit is in fact the equivalent class of the point X. One of the first things that we discussed in this course was the fact that there is a bijection between equivalent classes and partitions. In particular, we showed that equivalent classes form a partition of the set. Now we showed that equivalent class of X is simply the G orbit of X, and therefore the set of all the G orbits, which is the same as the set of all the equivalent classes, is a partition. Because this is an equivalent relation, we know that this is a partition of X, and that completes the proof. Okay, so far we discussed what the group action is. We discussed what G orbits are, and we showed that G orbits form a partition. The set of all the G orbits is denoted by X, and we say we are quotienting X by G from left, because G action is from left. We are looking at the factor of X by G from left, and we denote it by this. So please try to not get confused with set difference. Here we have to make sure and write down G a bit lower than X to avoid confusion with the set difference of G and X. So we are modding out, we are looking at the quotient of X by G, we are looking at the factor of X by G, we are looking at the G orbits of the action of G on the set X. And we just proved that this set, which consists of the set of all the G orbits, is a partition, and therefore when I add the cardinality of all the elements, so when I pick elements of this partition, when I add the cardinality of their elements, I end up getting the cardinality of the entire set X, because this is a partition. This is an important equality that we will be using again and again in this course. So cardinality of X is equal to summation of the cardinality of the orbits. So size of X, cardinality of X, is the same as the sum of cardinality of orbits, of G orbits. Okay, so another important relation that we will come back to this later. Remember, we had shown that two equivalent classes, this is equal to this one, precisely when X is equivalent to Y. This implies that the orbit of X under G, the G orbit of X is equal to the G orbit of Y precisely when Y is G similar to X. And that means, okay, let's write it down, Y is G similar to X, which means Y is G star X for some G. This is an important property that we will come back to later. In this video, a special case of this at least, and later in this course, in this generality. So two G orbits are equal precisely when the initial points are G similar to each other. We'll come back to this is Satan later. Let's see some examples now. Let's look at the action of the symmetric group S sub n on the set 1, 2, n. We know that for every A that I give you, the transposition 1A flips the order of 1 and A. In particular, it sends 1 to A. And therefore, if I let this transposition act on the point 1, I end up getting A, which means A is S sub n similar to 1. A is in the S sub n orbit of 1. Every point is similar to 1. Every point is similar, S sub n similar to 1. Therefore, there is only one S sub n orbit. That means this quotient, this factor, has only one element. If an action has only one orbit, we call it a transitive action. We say G acts transitively on the set X if it has only one G orbit, if every point is G similar to every other point. It means it has a lot of symmetries, right? So if it has only one G orbit, then we call the action transitive. Similarly, I can reformulate it and say that if I give you 2 points inside this set, they are G similar. There exists some element of the group which sends one to the other. So in that case, we say that the action is transitive. So every point is G similar to another one. In that case, the action is called transitive. For instance, as we discussed, the action of the symmetric group on the points 1 to n is a transitive action. When I look at the action of G on itself by left multiplication, again, let's recall that means that when G acts on the point X, I simply multiply G by X, and so that we call left multiplication, the action by left multiplication. Let's try to understand orbits of this. My claim is that this orbit is again transitive. I give you 2 points, x and y, and I want to act on x and reach to y. Acting means I want to multiply x by something, end up getting y. Okay, that something can be simply yx inverse. So for every y, yx inverse acting on the point x gives me yx inverse dot x. These guys cancel out. I end up getting y. And so y belongs to the g orbit of this action. So maybe I wanted to write down the star here. What I wrote is correct, but maybe I wanted to write a star because the action is given by star. So y belongs to the g orbit of x, and hence the action of g on itself by left multiplication is a transitive action. Now let's look at the action of g on itself by conjugation. So again, that means the element g acts on the point x by conjugating x by g. We have discussed that this is indeed a group action. Let's try to understand the g orbits. The g orbit of x consists of the points of this form, which is precisely the set of all the conjugates of x. We showed that the g orbits form a partition of the set x. So this means the set of all the conjugates form a partition of the group G. This G orbit is called the conjugacy class of X. Similar to equivalent class, here, because conjugation is an equivalent relation, we refer to this as the conjugacy class of X. So this is called the conjugacy class of X. And we denote it by CL standing for class, CL of X. So CL of X with capital C is the conjugacy class of X. And because the G orbits form a partition, we deduce that conjugacy classes form a partition of the group G. We'll come back to this partition later in the course. Maybe. So we get that conjugacy classes form a partition of the group G. Now, we've discussed that G acts on, but maybe before going, let me make a remark here as well. I have discussed that the two G orbits are equal if and only if y is G similar to X. So that means the conjugacy class of X is the same as conjugacy class of Y if and only if X and Y are conjugate of each other. It's useful to remember this. Okay, now we've seen that G acts on itself by left multiplication, and we've seen that if I have a group action for the group G, then I'm getting group actions for every subgroup of the group G. So because G acts on itself by left multiplication, a subgroup of G acts on G by left multiplication. So if H is a subgroup of G, then H acts on the group G by left multiplication. Again, what does that mean? This means H acts on the point X by simply multiplying it from left. We are getting a group action because G acts on itself by left multiplication and H is a subgroup. This we have discussed earlier. Now, what are the H orbits under this action? The H orbit of X is where we can get all the points that we can get after letting elements of the subgroup H act on the point X. Acting simply means multiplying. So this means, what are the points of the group G that we can get after multiplying elements of H from left by the point X? So we, so to speak, are shifting X from left by elements of H. When I say shift, I essentially mean that I'm multiplying by the element small h. So in this case, we are going to denote the H orbit simply by H dot X, because that's what we are doing. We are multiplying elements of H by X, so that's why we are going to use this notation, H dot X, instead of H star X. In this case, because the star is simply dot. And we are going to call this a right coset of H. The set of all the right cosets is going to be still denoted by G quotient by X, or factor of G by H, not X, H, from left. And this set consists of all these H orbits, and this is going to be a partition of the group G, because in general, orbits form a partition of the set that we are acting on. H is acting on the set G, and therefore the set of H orbits form a partition of the set G. In this case, H dot X is called a right coset of H. Now I'm putting emphasis on H, and I'm saying that I'm shifting H by X, and therefore I call it, because I'm doing it from right, I call it a right coset of H. So a right coset of H either can be achieved using this group action of H, and where we can get starting from X, or I can think about the set H and multiplying X from right. And in that case, that's why, because I'm multiplying from right, I'm going to call it a right coset of H. Okay, so now we want to understand this set of all the cosets and this particular partition that we get, G, and the quotient of G by H from left. So, or the factor of G by H from left. So that's, we call this set either the quotient of G by H from left, or the factor of G by H from left. It is simply the set of all the right H cosets. Right H cosets. So these right and left, please don't get confused. This left refers to from where I am acting on the group G. This right refers to how I am shifting the subgroup H. So I'm talking about right cosets of H. So co is like the same set, but from right I'm shifting it. And the left quotient, that means I'm letting H act on this from left. So elements of H are multiplied by elements of G from left. That's why I'm calling it left quotient, or quotient of G by H from left. Okay, let's see basic properties of this quotient and the right cosets. So G is a group, H is a subgroup. Now two cosets, two right cosets, are equal precisely when X times Y inverse from right belongs to H. So here, please do not multiply Y inverse from left. How can you remember this? You see, I have this equality h dot x, and you have this equality, you want to get rid of y. In order to get rid of y, you cannot multiply from left because h is here. H doesn't allow you to bring y close to x. You need to multiply y from right in order to attach it to x. So from this, you can get that I am multiplying x. I'm multiplying this equality from right by y inverse, and I end up getting this equality. Essentially, I'm shifting these sets by multiplying by elements, of the group, and then I need to multiply from right. This is one way of thinking about it. This way of thinking about it can help you to remember that y inverse should be on the right side and not on the left side. So the right coset hx is equal to the right coset hy precisely when x times y inverse belongs to h. Okay, this tells me under what condition these two cosets are equal. Next, we see that there is a bijection between h and its cosets. Essentially, I'm shifting it. I've mentioned this many times. So I just shift this element small h by x, and I go from small h to h dot x. And claim is that this is a bijection, and therefore cardinality of h is the same as cardinality of all of its right cosets. Now, if G is a finite group, all these cosets, which are h orbits, have the same cardinality, and they form a partition of the group G. Therefore, the cardinality of the group G is simply the number of h orbits times the cardinality of all of these orbits. They have the same cardinality, and that's the cardinality of h. So I get that cardinality of G is simply the number of h orbits times the cardinality of h. This is an extremely important equality. In particular, this implies that cardinality of every subgroup divides cardinality of the ambient group. This is what we call Lagrange's theorem. I'm going to write this separately and make more emphasis on this. But at the moment, let's try to understand it again, that if H is a subgroup of G, then the number of right H cosets times the cardinality of H gives me the cardinality of G. Okay, let's go through the proof. Let's start with part one. The right H coset given by X is simply the H orbit of X. Similarly, the right H coset H dot Y is the H orbit of Y. Now, H orbit of X is the equivalent class of X under H similarity. So this equality means that equivalent class of X under H similarity is equal. So this equality means that equivalent class of X under H similarity is the same as equivalent class of Y under H similarity. Again, we have seen that these two equivalent classes are equal precisely when X is in relation with Y. That means Y is H similar to X. So the right H coset given by X is the same as the right H coset given by Y, precisely when Y is H similar to X. But let's recall what H similar means. It means that I can reach to y by letting some element of h act on x. And acting here means that I have to multiply h from left by x for some h inside the subgroup. Let's manipulate it. Y is h times x. I'm going to isolate h. That means y times x inverse is h. So y x inverse is h. So y x inverse belongs to h. Okay, I could have done similar thing and said, and I could have done, because this is the same as saying that its inverse belongs to h, by taking inverse. So I get this way. Or I could have isolated, I could have written it like this, that this is the same as saying that h inverse is x dot y inverse. In either case, we get the desired result that these two cosets are equal precisely when one of them times inverse of the other one is inside h. One of the representatives times inverse of the other one is inside h. Okay, because it seems that we have used many results from the previous videos, let's see another more direct method which uses the things that we have already discussed, but not in a shell. I'm going to open up all the shells that we have used. So let's again see an alternative way of showing the same equality, the same conclusion. Suppose that the coset given by x is the same as the coset given by y. This is a set, this is a set. This means I have equality of two sets. This set consists of all the elements that are of the form some element of h times x. In particular, the neutral element which belongs to this times x is here. Neutral element times x is simply x, and that's supposed to be inside this set, and therefore it belongs to this set. So neutral element times x, which is x, belongs to the right coset of h using y. That's represented by y. So that means x belongs to h dot y. But an element here is of the form something inside h times y, something inside h times y. That means x is something inside h times y. So again, I'm going to isolate h, and I deduce that x is inverse of y, x times inverse of y is h, for something inside h. That implies that x times y inverse belongs to h. Okay, so far we showed that if these two right cosets are equal, then x times y inverse is inside h. Now I want to show the other way around. So I'm going to assume that x times y inverse is inside h, let's call it h naught, and I want to show that these two cosets are equal, and these are two sets. I need to show that something here is inside the other one, and vice versa. So let's start with some element here, and I want to show that it belongs to this one. So suppose z belongs to h dot y, and I want to show that it belongs to h dot x. What does it mean that it is inside h dot y? It means z is something here times y, something in h times y. Okay, but I want to show that it is also something in h times x. So I want to end with x. In order to end with x, I can do this trick. I can simply multiply x inverse and then x. So this way I end up with x. Now, am I lucky and this part is inside h? Okay, let's think about it. What do I know about x and y? I know that x y inverse is inside H. What's the connection between this and what we have over here? Let's think. Ah, this one is inverse of that one. This is precisely H naught inverse. And H times H naught inverse does belong to the subgroup H, so we are good. This implies that Z is something inside H, that's this one, times X. Okay, let's make it more formal. So Z, so far we know, is H times Y. Now my claim is that it is, okay, so this is precisely H times H naught inverse, H naught. So I'm not doing something special. I'm multiplying this guy by itself and canceling it out. This argument is essentially what I had in the other page, but this might seem slightly more tricky because here it's not clear why I consider to put H naught inverse, H naught in the middle. So in the previous line of logic, I suggested this because I want to show that this guy is something inside H that we don't know times X. Okay, in order to reach to having X at the end, it only makes sense to, I mean, or I can solve for this something over here, right? So I can solve for it and I see that it is H times Y times X inverse. So I can simply write it here. And now the question is, does this guy belong to H? And this is H times H naught inverse, and it does belong to H. Now here is an alternative way that I have written over here. I'm simply multiplying by H naught inverse and canceling it out. H naught is X times Y inverse. This part is inside H, and X times Y inverse times Y is simply X, and we get the same result that we have over here. So Z does belong to H dot X. Now I want to go the other way around. Let's start with some point inside H dot X. I want to show that it is in H dot Y. So this means Z is something inside H times X. Again, I want to write this as something times Y. So if I solve for that something, we see that it is this one. And this is simply H naught. And this does belong to H. Here is an alternative method. So again, I multiply this time by H naught and cancel it out in the middle. And I notice that H naught inverse is X times Y inverse inverse. And that is Y times X inverse. This X inverse cancels out X. And I get something inside H times Y. And that's exactly what we have over here as well. In either case, we get that Z belongs to H dot Y. Everything inside H dot X is inside H dot Y. Everything inside H dot Y is inside H dot X. Therefore, they are equal. And that's an alternative proof for this important result that H dot X is equal to H dot Y if and only if X dot Y inverse belongs to H. Now let's see why we have a bijection between a subgroup and its cosets. And the bijection is simply given by shifting it by X, so multiplying H from right by X. Okay, so why is it well defined? Of course, I'm getting a point here because of the way that we are defining. And moreover, every point here is of this form. So this is definitely surjective. Now, why is it injective? It's because of the cancellation law. Because if f of h1 equals to f of h2, that implies h1 dot x is the same as h2 dot x. I can cancel out these x's because of the cancellation law. I deduce that H1 is H2. So F is injective, F is surjective, and therefore F is a bijection. Oops. So that implies that cardinality of every subgroup is equal to cardinality of every one of its cosets, right cosets. Now, because of the equality that we had earlier, that the space can be written as the cardinality of the space can be written as sum of cardinality of orbits. This we had for any group action. Now here we have proved that every orbit has the same cardinality as cardinality of the subgroup H. So I can replace these ones by cardinality of H. Now I'm adding the same number again and again and again and again. You see, this number doesn't depend on the choice of this H orbit. That means that I'm adding the same thing how many times? The number of elements of this set times. That means cardinality of G is simply cardinality of the number of H orbits times cardinality of H. So cardinality of the quotient of G by H from left times cardinality of H. That's cardinality of G. This number we are going to call the index of H in G. Okay. So this cardinality, the cardinality of the set of all the right H cosets, is called the index of H in G. And we are going to denote this by this. So square bracket G 2 dots H square bracket. So that is called the index of H in G. And what we proved shows that cardinality of G is simply index of H in G times cardinality of H. In particular, cardinality of H divides cardinality of G. This is Lagrange's theorem. This is an extremely important theorem. We will be using this result many times. Here is an important corollary of Lagrange's theorem. So if I tell you that G is a finite group, I can look at the cyclic subgroups of G. So I can start with an arbitrary element of the group. And then by looking at the cyclic subgroup generated by G, I get a subgroup of G whose cardinality is precisely the order of the element G. And therefore, by Lagrange's theorem, order of G divides cardinality of the group. And therefore, G raised to the power of the cardinality of the group is always the neutral element. No matter what the group is, no matter what the element G is, when I raise G to the power of the cardinality of the group, I end up getting the neutral element of the group. Okay, let's go through the proof. This is an amazing corollary of the Lagrange's theorem. So let's see how we can show this. So again, for a cyclic group, we have proved that cardinality of a group generated by G is equal to the order of that element. By Lagrange's theorem, cardinality of a subgroup divides cardinality of the group. So cardinality of the cyclic group divides cardinality of the group G. And therefore, order of G divides cardinality of this group. Now remember, if order of G is some number D, then G raised to some power, some integer power, is the neutral element precisely when this D divides N. Now, when I tell you that order of G divides cardinality of the group, you deduce that G raised to power this integer is the neutral element, and that's exactly what we claimed. So again, let's repeat this. If G is a finite group and small g is an element of this finite group, then order of G divides cardinality of this finite group, and G raised to power the cardinality of the group is the neutral element of the group. These are important facts that we deduced using Lagrange's theorem. They can have many implications. So for instance, the following is an application of Lagrange's theorem to classical number theory using the result that we just proved. It's called Euler's theorem. Suppose n is a positive integer. I am going to look at the multiplicative group of z sub n, essentially. But before that, let's write it in a classical setting. Suppose a is an integer, which is co-prime with n. So GCD of a and n is 1. Then, if I raise a to power the Euler phi function of n, this is going to be definitely congruent to 1 mod n. This is Euler's theorem. This is why, in fact, this function is called Euler's phi function. Okay, let's see why this is the case. We are going to consider the multiplicative function of z sub and the multiplicative group of units of integers modulo n. Remember, this group has precisely phi of n elements. It consists of residue classes where a and n are co-prime. In particular, because GCD of a and n is 1, the residue class of a belongs to this group. In the previous theorem, we proved that in any group G, G raised to power the cardinality of the group is the neutral element. Now I'm going to use this result for the multiplicative group of z sub n and the residue class of A. So residue class of A raised to power the cardinality of this group is the neutral element. Cardinality of this group is the Euler phi function. And so the residue class of A raised to power phi of n is the residue class of 1. Two residue classes are equal precisely when these numbers are congruent modulo n. So we get the desired congruence relation. Now let's use Euler's theorem to show Fermat's little theorem. What is Fermat's little theorem? If p is prime, then for every integer a raised to power p is congruent to a modulo p. Okay, let's see why this is the case. If a is congruent to 0 mod p, there is nothing to show because both sides are indeed 0 mod p. So we get what we want. Now assume a is not 0 mod p. Then the residue class of a is actually in the group of units mod p that we showed. Or alternatively, we can say, but we have to argue why this is the case, that the a and p are co-prime. Here, either you can use the definition of prime to show this, or you can use the fact that this is inside ZP cross if P is prime and A is not 0. So either you can use this one, or you can show this directly using the fact that P is prime. In either case, you deduce that A and P are co-prime, and therefore by Euler's theorem, A raised to power phi of P is 1 mod P. Remember, P is prime, and therefore phi of P, we can also argue it as we did here, is precisely P minus 1. And therefore, A raised to power P minus 1 is 1 mod P if A is not 0 modulo P. If it is 0, A to the P is A. If it's not 0, A to P minus 1 is 1. I multiply both sides by A. I deduce that A to the P is A in this case as well. In either case, we get Fermat's little theorem. Let's see another example. We want to find cardinality of the alternating group and the index of the alternating group in the symmetric group when n is at least 2. N is 1 is not interesting because in that case, S sub 1 has only one element. Okay, so claim is that sigma is even. If sigma is even, then A sub n sigma is essentially A sub n. If sigma is odd, then this coset is A sub n, the coset that's given by this transposition, this permutation 1, 2, this transposition that's given by 1, 2. Let's see why this is the case. Remember that two cosets, hx and hy, are equal precisely when xy inverse belongs to h. So to show is this equality, I need to argue that sigma times inverse of identity is inside a sub n, but that is the case. Because sigma is inside a sub n, this is inside a sub n, therefore these two cosets are equal, and that's exactly what we wanted to show. Now if sigma is odd, sine of sigma is -1, therefore sine of sigma times this transposition is sine of sigma times sine of transposition, -1 times -1, I'm getting 1. That means that this product is inside a sub n, and therefore, remember, every transposition is inverse of itself, so this times the inverse of this transposition is inside a sub n. Again, using this criterion, we deduce that the coset given by sigma and the coset given by the transposition 1, 2 are the same. Altogether, I'm deducing that there are only two cosets, and therefore the set of all the cosets has exactly two elements. One of them is a sub n, the other one is a sub n 1, 2. Remember, this is odd, this is even, so their product is odd, and therefore it doesn't belong. These two cosets are not equal to each other. Let me write this down as well. Notice that a sub n sigma is equal to a sub n tau if and only if sigma tau inverse is inside a sub n, and that happens precisely when sine of sigma is the same as sine of tau, so they have to have the same parity. So in particular, if I give you an odd representative, it cannot give me the same coset as an even representative. So these two are different cosets. Altogether, I deduce that there are precisely two elements inside this partition, and so the index of the alternating group in the symmetric group is exactly 2. Therefore, by Lagrange's theorem, because I know cardinality of the symmetric group is index of the alternating group times cardinality of the alternating group, I end up getting that the cardinality of the even permutations is n factorial divided by 2. Half of the permutations are even and half of them are odd. Okay, so let's see the final example. It is related to index of subgroups in dihedral group. So remember that in the dihedral group, we have these two specific symmetries of the n-gon. One of them is kind of rotation, sends x to x plus 1. And the other one is kind of reflection, that sends x to -x. We want to find the index of the symmetric group, the cyclic group generated by sigma in this dihedral group, and the index of the cyclic group generated by tau in this group. Notice that sigma to the m applied to x is x plus the residue class of m. That means sigma to the m is identity precisely when this number is 0. That means sigma to the m is identity exactly when n divides m. And so this happens exactly when this happens. That means order of sigma is n. Therefore, cardinality of the group generated by sigma is simply n. And so the index of the cyclic group in the dihedral group is, using Lagrange's theorem, is cardinality of this guy divided by cardinality of this guy. So it's cardinality of the dihedral group divided by cardinality of the cyclic group. Cardinality of a cyclic group is equal to the order of the generator, order of a generator, order of sigma is n, I get 2n over n, that is 2. So there are only 2 cosets of the cyclic group sigma in the dihedral group. In fact, we know what the cosets are. So they are sigma and sigma tau. These are the only 2 cosets. We know that this form a partition of d sub 2n, and that's why this is the set of all the cosets. Now, how about tau? We know tau squared is identity. Tau itself is not identity, and therefore the order of tau is 2. And so the cyclic group generated by tau has only 2 elements. Therefore, by Lagrange's theorem, the index of the subgroup in the dihedral group is the cardinality of the dihedral group divided by the cardinality of the cyclic group generated by tau, and that is 2n divided by 2, which is n. So we learned about group action, we learned about orbits, we saw how orbits partition the set X that we are acting on, we learned about left multiplication, we learned how group of symmetries act on a point, on the object, we learned about conjugation action, we learned how an action induces an action of subgroups. We use this to define left multiplication of a subgroup on a group G. The H orbit under that action is called a right H coset. We use this knowledge to deduce that right H cosets form a partition of the ambient group. We showed that all the right H cosets have the same cardinality. Deduce that if G is a finite group, cardinality or order of G is equal to the order of the subgroup times the number of H cosets. In particular, for a finite group G, cardinality of every subgroup is a divisor of the cardinality of the group. From this, we deduced order of every finite group divides cardinality of the group, and therefore G raised to the power of the cardinality of the group is always the neutral element of the group. Using this, we deduced Euler's theorem in classical arithmetic and Fermat's little theorem. And we saw some examples in the case of symmetric group and dihedral group. We continue in the next video later.